All right. I'm really excited to talk to you all today about what the Landscapes and Seascapes working group of SZ4D has been developing over the past couple of years since early 2020. And so I'm going to try to kind of summarize what we've been working on as a working group and provide some examples that will hopefully show you some of the cool science that we hope to do related to the science questions. So I only have 15 minutes, so I can't talk about all of the things that we've been working on. Let's see. Next. But I want to start by, I think this, okay, yeah, here we go. So the Landscapes and Seascapes working group was charged with imagining a broad, inclusive research program to study the science of geohazards across subduction landscapes and seascapes. So that's obviously a very big charge. And so we collected a group of like 25 working group members from the geomorphology, tectonics, structural geology, marine seismology, marine science, and volcanology communities to try and kind of put some teeth behind that charge and to try to really represent our science community and what they thought would be interesting and transformative science questions and problems in this area of geohazards across subduction zone landscapes and seascapes. So we spent at least a portion of our time developing these primary research questions that were intentionally very broad and overreaching across many different subdisciplines in our field. And the first question that we came up with, question one, is how do events within Earth's atmosphere, hydrosphere, and solid Earth generate and transport sediment across subduction zone land and seascapes? And so I'm going to give you some examples of what we mean by these broad science questions in the next slides. But the second question that we came up with was what fraction of a subduction zone's energy budget goes into building and shaping subduction zone landscapes and seascapes? And so both of these questions allowed us to develop some broad working hypotheses. And so here's just an example of a broad working hypothesis that we came up with for question one. Sediment generation and transport is controlled by the frequency of drivers that initiate and mobilize sediment. That's just an example of a hypothesis. And so if we pose this hypothesis, we can say when large storms occur frequently, landslide-related hill slope transport and their hazards could be dominated by atmospheric events. In areas where storms occur less frequently, earthquake shaking or intense volcanic rock weathering may play a more significant role. And so that's what this diagram is showing here, where through time, the rates at which events occur depend on the frequency of earthquakes and storms and volcanic eruptions and how they interact with one another. So you can imagine that you could have cascading impacts where if you have storms that occur frequently in time to one another, that they would have a larger impact on the landscape than an infrequent earthquake. Okay, so the second example, broad working hypothesis for question two, is that the subduction zone system has these energetic inputs and outputs, inputs and sinks, and the energy budget framework allows us to integrate these processes to investigate their interplay. So one example hypothesis would be that the style of upper plate deformation is regulated by plate motions and coupling along the megathrust, elastic and inelastic deformation processes in the upper plate, body forces generated by topography, and the rheological configuration of the upper plate. Obviously, that's a lot of different factors that are at play. And so one way that we've talked about how to isolate those various factors and their importance is through comparison sites. And so the LNS group's experimental design is very much based on selecting paired subduction zone segments where you can control for as best as possible one variable and leave the others and let the others vary. So an example would be if you have subduction zone segments with constant solid earth properties but different climates, or you can have a subduction zone segment with constant climate and different other properties such as plate tectonic, volcanic parameters, but different mean slopes. So I'm not going to really be able to talk about all of the lengthy discussions that we had about geography and how we came to the conclusions that Chile was a great place to put our focus site or focus our efforts. But I just want to point out that Cascadia was considered an ideal comparison site for LNS to carry out our notional experiments, in large part because of the gradients in rainfall. And so the slide on the, or the image on the right shows the strong change in orographic rainfall that occurs at about 32 degrees south in Chile. And so that really sets up a great example of where you can hold one factor constant and then allow others to vary. So I wanted to point that out as a really like a leverageable component of this margin. And so obviously also there are other differences and similarities between Cascadia and Chile that you could also leverage. Like they have different topography in the forearc, they have different plate ages, et cetera, et cetera. Another one I'd like to point out is that there are end member variations in the amount of trench sediment and the size of the offshore accretionary prism between those two examples. Okay, so I think we've all heard the word traceability matrix probably more today than we ever had in the past, for those of you that aren't familiar with this concept. So I don't want to go through and describe it again, but here's an example of the traceability matrix that LNS used to define their data, infrastructure, and computational requirements. And so you can see we have the question on the left, how do events within Earth's hydrosphere, et cetera, et cetera. And then we had various other columns that asked other questions that were kind of sub-questions of that larger science goal. And so this is just an example of the very first row of our traceability matrix. Ours was similarly large to Damien's, and it could probably take up a lot of room that you couldn't see on the slide. But you can see that we identified our observables and measurement requirements in the same way. And this is just an example of how we came up with the need for high resolution bathymetry and INSAR. Okay, so throughout this process, this is just kind of a laundry list of some of our key basic data needs to address the science questions. High resolution topography and bathymetry was a very key data need. High quality geologic data, as well as repeat optical and topographic surveys. Geochronology and high throughput geochronology was considered very important, as well as different types of ways to date either or get dates and rates using various cosmogenic techniques and geodesy as well. Okay, so some of the key infrastructural needs that we identified were robust cyber infrastructure and modeling. And so this is going to be necessary to kind of organize, distribute, and archive our data. And we also identified that we really need numerical model development and integration. If we want to model at the scale of an entire subduction zone, we don't really know how to do that right now. And we need to work with the people at MCS that know how to do that. And we need to develop efficient physics-based forward models to do that. I mentioned before that we need to develop high throughput geochronologic facilities, and they need to be able to meet the demands of the project, but while also maintaining kind of uniform data quality. You don't want one PI to use one lab, another PI to use different lab, and the data quality is need to be standardized. The last one that we identified was integrated field-based experiments, instrumentation, and observatories. So we really want to coordinate our field-based campaigns to leverage the SURF array, which Emily talked about at the very first talk, and I'll talk about on my next slide. But the LNS group came up with a design of a environmental change detection array called SURF array that can only really be made meaningful if it's coordinated with field-based campaigns. And so the next slide is going to show you a little bit more detail of what that SURF array is like. So the image on the right is showing two watersheds, and each of the dots are showing stations. And so we have hill slope stations that can measure precipitation, soil moisture, temperature, and microseismicity. And we have various different levels of like resolution associated with those stations that are shown, the distribution of which is shown on the right. We also have stream stations. And so these are going to measure things like water discharge and suspended sediment, freshwater chemistry, bed load transport, and turbidity. So we have a backbone array, which is shown on the bottom left, that will have the kind of a low end hill slope station. But then we also have two kind of tricked out watersheds that are very heavily instrumented that can give us information about all the data sets that I listed on the left. So this stationary network can be co-located with a lot of the FEC and MDE array instrumentation, but it will also be supplemented by a kind of movable network for a rapid response type scenario. Okay, so I know that cross-cutting science is going to be talked about tomorrow, and so I don't want to kind of take over that discussion, but I wanted to leave you with one of the kind of really cool cross-cutting science questions that I think LNS is hoping to address with their initiatives. And so that science question is, how do cascading sequences of events impact subduction zone hazards? So you can imagine that either earthquakes or eruptions can initiate mass wasting events. And this single mass wasting event can trigger downstream effects such as flood, accretion, or erosion. And these effects can disturb the landscape for a decade or even longer. And so this can cause like really long lasting damage to communities that can persist for decades. And that's what the three images on the right are showing: a community that's on the river terraces that has been impacted by a sudden landslide, which dams the upstream portions and causes a lot of mass wasting in the downstream portions. And initially that river is going to grade, but then later on it's going to size. So I just wanted to give this example of a cool kind of interplay between MDE type problems and LNS type problems. And so how are we going to really understand and predict or forecast these types of hazards? I would argue it requires an integrated field-based experiment, instrumentation, and modeling. So if you see on the image on the right, there are actually two volcanoes here in this one watershed compared to not shown in this on the left. And that was actually a deliberate design factor, in that if you have one watershed that has recent volcanic flow, the downstream effect of that can be measured by the surf array. And for example, channel width could change. And you can compare that effect to a watershed that does not have a recent volcanic flow. And so this array really needs to be accompanied by other measurements, such as the mapping of volcanic deposits by volcanologists, geomorphologists, and structural geologists. You need to measure sediment flux. The surf array can do that, but you also need to quantify hill slope strength and work with, geophysics of granular materials type scientists. And you need field geologies to go out and quantify incision and aggradation. So I'll just leave by saying that answering the LNS questions really requires this integrative, comprehensive, and holistic approach in a collective impact framework. And I'm really excited about us all working together so that we can answer these big science questions.